As neural networks rapidly expand into the trillions of parameters, the silicon to process them has become the most heavily constrained commodity in tech. This presentation slide shows NVIDIA's Blackwell B200 architecture. Notice the specific marketing claims here: a second-generation transformer engine and fifth-generation NVLink, promising massive generational leaps in inference speed and energy efficiency. But those throughput metrics come with a steep reality check, a massive 1,000-watt power draw per chip, and a severe premium acquisition cost, which raises a crucial question for engineering teams. Do you actually need to spend $30,000 to $40,000 per GPU to run your specific workloads? Depending on your deployment, discounted previous generation Hopper GPUs, or even standard CPUs, might offer a smarter financial path. We are going to map the exact technical trade-offs between CPUs, Hopper GPUs, and Blackwell GPUs to help you optimize your infrastructure purchasing. Buying AI infrastructure requires ignoring the maximum spec sheet and matching the hardware's mathematical architecture directly to your workload scale. A central processing unit executes highly complex instructions sequentially. It is built to solve one sophisticated problem at a time. This sequential design makes CPUs highly flexible. They handle irregular workflows and complex branching logic easily, drawing directly from standard system memory without needing specialized memory management. For traditional machine learning models like XGBoost, data preprocessing pipelines, or single-request edge inference, this makes CPUs incredibly cost-effective. But if you attempt to train a deep neural network sequentially, the process will take months. A graphics processing unit solves problems differently. It breaks operations into tiny fragments and distributes them across thousands of smaller CUDA cores to process simultaneously. Applying this parallel processing architecture to massive datasets collapses deep learning training schedules from months down to hours. That speed comes with steep hardware acquisition costs, massive electricity demands, and the requirement to build within specialized programming frameworks like CUDA. The choice between a CPU and GPU hinges entirely on whether your application relies on sequential logic or massive parallel matrix multiplication. This diagram illustrates the precision trade-off. On the left, a standard CUDA core calculates 64-bit floating point numbers sequentially. On the right, a Tensor core processes an entire 4x4 matrix at once. Full 64-bit precision is necessary for rigorous scientific workloads like fluid dynamics or quantum chemistry, where exact decimal accuracy matters. But for neural networks, it consumes far too much time and energy. Tensor cores bypass this by executing mixed precision operations, multiplying and adding entire matrices in a single clock cycle, utilizing lower precision formats like 8-bit or 4-bit floating point. Dropping from 16-bit to 8-bit precision halves the memory footprint of the data. This allows the chip to process significantly larger batches, sharply accelerating training throughput. By cutting the precision down, you sacrifice strict numerical accuracy. You cannot use these low-precision modes for a high-fidelity weather simulation. But a generative AI model does not require perfect decimal accuracy to correctly calculate the statistical probability of the next word or pixel. Modern hardware scaling is achieved primarily by aggressively sacrificing mathematical precision to maximize data throughput. This is the physical GH100 silicon die, the foundation of NVIDIA's Hopper architecture. Released in 2022, the H100 is the mature workhorse of the AI industry, and its acquisition costs are steadily dropping. It provides robust 8-bit precision for fine-tuning, but its 80 gigabytes of memory creates severe bottlenecks when trying to run models with massive context windows. This image shows the massive scale of the multi-GPU Blackwell rack component. The B200 architecture upgrades capacity to 192 gigabytes of high-bandwidth memory per chip and introduces native 4-bit floating point precision. It also integrates 5th-generation NVLink, a fabric interconnect that allows up to 576 Blackwell GPUs to share data at 1.8 terabytes per second, creating a single unified memory pool. This generates massive inference throughput for trillion-parameter models. But deploying these 1,000-watt dual-die chips requires a complete overhaul of your data center's power and cooling infrastructure. To make room for these AI-specific tensor enhancements on the silicon, NVIDIA actually reduced the raw double precision 64-bit performance compared to the older Hopper chips. Upgrading to Blackwell focuses less on raw compute speed and more on eliminating memory bottlenecks, allowing entire server racks to operate as a unified system. Hardware is no longer one-size-fits-all. Architectural choices must be dictated by your parameter scale and capital constraints. This flowchart maps optimal hardware paths based on workload size, precision, and budget constraints. Let's trace the routes. If your team runs data preprocessing, traditional machine learning, or low-latency edge inference, bypass GPUs entirely. CPUs offer the highest efficiency here. For startups fine-tuning models under 70 billion parameters, or labs executing high-fidelity physics simulations, the H100 is the correct target. It delivers mature software support, superior double-precision math capabilities, and favorable pricing on cloud and secondary markets. If deploying frontier language models exceeding 100 billion parameters or massive mixture of expert architectures, you will hit Hopper's memory limits. In hyperscale environments, the B200's initial hardware premium is offset by 4-bit throughput and massive memory pooling, drastically lowering long-term cost. Successful AI infrastructure scaling requires ignoring marketing cycles and acquiring the specific mathematical processing power your deployment actually demands.